evening everyone. This is and I will be taking your thermodynamics TS shift for this semester, and these classes will begin from 6 and it will end at 8 at every Tuesday. So uh, let us in this course what we will do is we will uh, solve problems that will be helpful for you in solving the various assignment questions that are given in your theoretical course. So let's move it. I am going to share my screen. This will take some time, so and then we'll start it. Okay, so let us move to the presentation. Yeah, so this is me, Thananka Sutia, and here I will be trying to solve these various sums that are related to this course. But before that, let me go to quickly give a revision of what will be required for solving the week 1 assignment. So first of all, what is a system? So system is something with it's the matter that we want to study, or that is the interest of our study. So defining a system is very important if you want to solve any thermodynamic question. Because if you change the system, the problem will totally get changed, because there may be mass flow interaction between one system. But if that same system is encompassed, if it is enclosed within another system, then that becomes an internal part of a system. So if you take the whole as a whole, you will not you will get a different answer. So taking the system is very important to us. Suppose and then next is surrounding is what? Everything that is external to the system is the surrounding. Let me use the pen. Suppose okay, thickness, yeah. Suppose this is the one, this is a box, any arbitrary box, okay, and which contains some matter. I am not telling whether it is a fluid, I am not telling whether it is a liquid, I am not telling whether it is a gas. It's maybe anything, some any arbitrary matter is present here. And if we want to study the change in temperature or whatever parameter of this matter contained within this box, then this box will be our system, and whatever is external to this box, it will be our surroundings. Okay, the vice versa is also true. Suppose we do not want to study what is happening inside the box, we are only concerned what is happening outside the box, then outside the box becomes our surroundings, and inside whatever it is there, that is the box totally outside whatever it is there, it becomes our systems, because that is the our area of interest. And inside whatever it is there in the box, that will be our surrounding. Now this system and this surrounding, they are separated by a boundary. Now this boundary may be real or imaginary. When I will start solving the problems, I will say what type of boundary is real or what type of boundary is imaginary. So you can see that, suppose this is the environment and this is my box, so that is inside this matter. So this box is my system and environment is my surrounding. If I am concerned about the properties that are concerned about the change in properties or the processes undergone by the matter inside the box, then it's my system, and these two will be separated by a boundary, and this boundary may be real or imaginary. Okay, now what is a universe? Now if you add both the system and the surroundings, that means the system and the surroundings, they are togetherly called as the universe. Okay, so system and the surrounding, they are togetherly called as universe. So whatever exchange is happening, it is happening always inside that universe. Now next is what is heat? heat is nothing but it is a form of energy, okay, and it is a form of energy that takes place when there is a temperature difference. Remember, if there is no any temperature difference between any two bodies, then heat transfer will never take place. Okay, suppose this is a body placed at A, this is a body at B, and let us say that I am connecting this two via a another rod, or you can say that I'm just simply putting these two aside together. So this is the body A and this is the body B. Now if the body A has a higher temperature than body B, then heat will always flow from A to B. But if the body A is equal to the temperature at the body B, then heat will not flow. So this means that it is an energy which is taking place, which transfers takes place when there is a temperature difference between any 2 points within the system or within the universe. Now one thing should be kept in mind, that heat is always a boundary phenomenon. Heat is always a boundary phenomenon. That means whatever heat transfer you are experiencing, you will be only experiencing this transfer, sorry, whatever, okay, whatever heat you will be getting, yeah, sorry, whatever heat you will be getting, you will be getting only because only at the boundary. Now the most important part is the sign convention for heat. Now if you add any heat to the system, then you have to take it as positive, and if you remove heat from the system, then you have to take it as negative. Okay, another is the work. Now work is also a form of energy, but the definition of work is such that, suppose this is a system, okay, and I mean, sorry, this whole thing is a system, and inside this there is some gases, there is a gas. Now if suppose whatever effect is going on inside this system, I can transfer this, uh, whatever effect is going on, I can transfer this in lifting a weight of the surrounding, lifting a weight of the surrounding. Then this, whatever effect is called, this is called the work. That is means that work is done by a system on the surrounding if the sole effect on the surrounding is, or it can be equivalent to the raising of the weight. Okay, now this might be a critical thing to understand. The only thing that you should remember is that you already know that heat is the form of energy which takes place when there is a transfer of which takes place when there is a temperature difference between two bodies. Now if any form of energy that takes place across a system boundary and that is not due to a temperature difference, then we can say it as a work. That means whatever energy transfer takes place that is not because of the temperature difference between the two bodies, then that energy transfer we can tell it as a work transfer. Now the point to be noted here is that work is also a boundary phenomenon. Okay, work is also a boundary phenomenon. Now suppose if the system does the work, then my work done is positive, and if work is done on the system, then my work is negative. Now these two will be very useful for us if you will be solving numericals. Okay, now we have seen, we have learned what is a system, we have seen what is heat, we have seen what is work. Now let us see what are the different types of system that is available in thermodynamics. Okay, now the first type of system that we have is the open system. The open system is one where mass flow across the system boundary takes place. Okay, and there may or may not be energy transfer, but mass flow is a must. For example, suppose this is my system. Now right now, how can I say that this is my system? Because of this boundary which I am talking about. Now this will be very very clear. I will come back to this again when I will be solving the problems. Now just now think this is my system. Okay, now suppose mass is coming in, or suppose mass is going out. Okay, I'm not talking anything about energy transfer. Suppose mass is coming in and suppose mass is going out. Now such type of mass transfer, if it is take place, then this type of systems, we call this type of systems as open system. Now control volume approach is used to solve the problems related to open system. Forget about this line, I will come back when I will solve a problem related to systems. Okay, now these are my open systems. Okay, insert new slide, blank. Now what is a closed system? A closed system is one where mass flow does not take place, but there is energy flow across it. Okay, and remember, these are all I'm talking about the boundary. That means this black colored box, that is nothing but my system boundary, the boundary line that is the separating between, that is separating my system and my surrounding. Okay, now if no mass flow takes place through the boundary. Now you may be confused about, suppose this is an electrical wire and electrons are always flowing across it. Okay, now if I consider the electric wire as my system, this is an electric wire and these are my electrons flowing. Okay, now electrons are always flowing. Now if I consider the electric wire as my system, okay, consider wire as system, then no mass flow through the boundary. This is the one which you should keep in mind. That means if my wire has electrons and it is flowing, so that is why defining system is very very important, and it is the very first step in solving a thermodynamical problem. Okay, now what is a closed system? A closed system is one in which there is no mass transfer takes place from the boundary. There may be mass transfer inside one from one place to another, because we always know that molecules are in random motion. We know this, that in molecular motion cannot be stopped, and if molecular motion is stopped, then it is an absolute zero condition, which is a hypothetical situation. So molecules are always moving from one place to another, and we are considering this entire box that contains these molecules as my system, and no part of the this is coming out of my system. So that is why I am considering this as my what you call I'm considering then if no mass flows takes place from this into or out of the system, then this I call it as my this my call is as the closed system. But there may be energy transfer takes place. For example, I am heating this from inside, or by via whatever phenomenon heat is going out. I am taking symbol Q for heat and W for work. For whatever phenomena heat transfer is taking place or it is going out, then energy transfer is taking place from the boundary, and as a result of which this can be termed as a closed system. Okay, admit, fine. Please let me know if someone is there in the lobby, because I cannot go back to the screen. Okay, hello Lalit, can you hear me? Hello, hello.
Yes, sir.
Yeah, can you see my screen?
Yes, sir.
Okay, fine. I was just discussing. You can go through the video because I will upload it in the YouTube anyhow. Okay, just starting with basics, whatever you have learned in the first class. Okay. Now,
Okay,
uh,
sir.
let us try to solve this problem. Now, consider the boiling of water in a vessel as shown. There are three conditions which I am giving you. That three different conditions. So, in this, you have to find out the mass flow through the system, the heat flow through the system, and the work flow through the system. Okay. So, first of all, uh, let us see case 1. So case 1 is nothing but this entire thing is open and you are heating from the bottom. Okay, now if you are heating from the bottom, first of all let us check what are the different types of mass transfer taking place. So you know that if you are providing heat from this one, that after some time, and since this is not closed from the top, so water can evaporate out. So that is why mass transfer mass transfer occurs at the whatever you can say position A. Okay, the at A, you can say that mass transfer takes place at A, or you can say that mass transfer from the system to the surrounding take place through this A. I mean, A is just a plane. Okay, it's not a point, it's just a plane. Then next is what is telling, it's asking about the heat transfer. So you know that you are putting input heat from the down, so heat is coming from this side. Now heat can flow from the all the lateral boundaries. Okay, since this is a three-dimensional figure, I can not show you as the three dimension. I just, even if it was a box, then say heat would have been flowing from all the directions outside. Okay, only from the bottom heat would have been in the input. Have you understood this one? So heat goes out goes out laterally in all directions, also in the top, also in the top, and heat comes inside the system from bottom. Okay, now the third one is the work done. Now uh, work done, what was the definition of work done? And the work done definition was that if you can convert whatever thing is happening inside the system into raising a weight in the surroundings, then this is called a work done. Basically that means is that if you consider, I mean, whatever you call this, is this will be my system. No, this liquid will be my system. Then this movement of the system boundary, it will be doing some work. It will be producing some displacement. So based on that displacement, the work will be done. But now I have given you this one as the entire system. Yes or no? This whole, including this container, I have given you the entire system. So the container is not at all displaced, neither is boundary is displaced. So that's why there is no work interaction takes place. No work interaction between system and surroundings. Okay, any doubt?
Yes, sir.
Okay. Okay, now let us come to the second question. Now this is just a modification of the first question. Here, instead of it is an open, okay, one more thing is there, whether you will use it in a control volume approach or a control mass approach. Remember, control volume approach we do when we will be dealing with problems of open system, and control mass approach we will be doing when we will be dealing with problems of closed system. That is feasible. It is not that if you do not take control mass approach in open system, oh sorry, in closed system, then it will be a problem. It will not be a problem, just the calculations will be too much. Okay, so it is better we do control mass. Let me write once again. Control volume we use for closed system. I'm sorry, control volume for open system, and control mass we do for closed system. Okay, so since this is an open system, why it is an open system? Because the mass is going out of the system anyhow, so that is why this is an open system. And in open system it is preferable if we do a control volume approach. Okay, now the next one, we have just modified the question as, say there was, instead of open, it was totally closed by a lid, and this is a fixed lid, it cannot move. Okay, and the same thing, you are putting energy or you are putting heat from below. The same heat transfer will be there from all sides, so there will be no change in the heat transfer as it was there in the first case. But only thing is that there will also be no any mass transfer. So what type of system it is? It is basically a closed system, and if you have a closed system, you can do a control mass approach. Okay, and this will be very very useful if you do control mass approach, because the lead is also fixed. That means this mass will be fixed, and it will be fixed in its position only. It will not at all move from here and there. Okay, later on when the course will progress, you will understand what will happen inside. Okay, what will happen inside if you close, then what will increase then. You are, because energy can neither be created nor be destroyed, you know that. So if you are constantly putting energy inside, what is going on inside, you will understand as the course progress. No, I'm not able to see who are coming. Okay, fine. Now next one, just any doubt in this B question? I mean the fixed lead. If not, then let us move to the third part, which is an interesting one. Now this is not a fixed lead anymore. This lead can move. That means think it as a piston. There are whatever it may be, any fluid. Okay, I'm not telling it as water. Normally people thinks water because we see most of the time water, so you think it is a water, but think it may be any gas also, and you are heating from below, and this piston or whatever lead, it is covering the container, it is a movable. Okay, now if you supply heat, what will happen? This particles, or if it is a gas, it will expand it very fast, and it will push it, and say that there is some limiter, that it this there are some limiter. You may ask that, oh sir, that this lead, it will go outside the container. No, I have put two fixtures there. Okay, so that means this can move, and it can move to a maximum limit of here. Now what type of system is it? Is it a closed system or is it an open system? That is the very first question it should come to your mind. Is it a closed system or is it an open system? Now first of all, there is no any mass transfer that is taking place between the system and the surrounding, so this is always a closed system. Okay, now next, since this is a closed system, we can apply what? Control mass approach. But here, suppose I am telling you, instead of this one, this can be thought of as another thing also. The other things will be exactly same, okay, as it was in the B case, because there will be no mass transfer between the system and the surrounding. Heat transfer will take place from entire this one, what you call from all the sides. Input will be only from this side and output will be from the rest of the sides of the container. And the third part was that work transfer, it will be always be 0. And the fourth one here, but here what you call now, that control volume approach or control mass approach. Now think about this as uh, let me insert. Okay, I think someone else is coming. No, okay, someone else is coming. No, okay. Now think about this one as a pipe, as a pipe flowing, as a okay, it is flowing. And suppose uh, this would have been like this one, that this was my movable piston. Okay, now this is the same thing. And from here I am putting, I mean, initially the fluid or liquid or gas, whatever, it was in a stable state, or sorry, it was in a fixed state. After I have applied the heat energy from this side, this started to expand and it started to move. And this is an infinitely long cylinder. Okay, here I have placed it between two rigid supports so that it will not cross this boundary. But in this case, this can move to its infinite length, whatever its length is. So in this case, this is, if I take the entire container as my system, then it is a closed system. And it is very good if I apply this one as what you call control mass approach. But what if I am only interested in this part of the region, okay, in this part of the container, then this becomes my open system. And at the same time I am applying this one as the control volume approach. Okay, so the entire thing, whether you can apply a control volume approach, whether this is an closed system, whether this is an open system, it depends on the selection of your system. So be very, very careful while you are selecting your system. So if no doubt, I will be moving to the next question. I will give you 2 minutes. If you can solve this and say me quickly the answers. Okay, if you solve, you can just unmute and you can give. You, if you do not understand the question, please let me know. It has two a chamber, it contains two gases and they are separated by a membrane. Okay, don't think about what type of material of this membrane is there. So whatever interactions is given, it is the heat interactions are given. So calculate the net heat gain or loss if you take A as the system, if you take B as the system, and if you take A and B together as the system. Okay,
Hello, sir.
yeah, hello. Hello.
Sir, this session is available after the meeting also.
Yes, yes,
Means,
yes, yes.
Any,
Yes. I will upload this in YouTube. Don't worry. Okay. So you will get
sir,
the.
can share
Hello.
share the link. Sir, can you share the link, sir, for that one?
Yes. I will share. Definitely, I will share. Don't worry. Okay.
Okay. Previous lectures are available, sir.
Yeah. I will. No, this is the first session of my tutorial classes. So I will share the my slides as well as I will share the videos with you. Don't worry for them. Okay.
Okay, thank you.
Okay. Please, if you can solve this or anyone can answer. Okay, let me then unmute everything. So what is given? It is given the heat interactions. In case 1, you should not worry about what is there. You should only worry about the system, and my system is this A. Okay, and my system is A. Now I am focusing on this A. And we know that heat, if it is added to the system, it is positive, and heat, if it is removed from the system, it is negative. Okay, now heat is a boundary phenomenon. So again, once again, we have to only worry about what is happening inside the boundary. Remember, you are, if you are you are a BTech student, probably you all people, and you will be giving examinations like gate. These are the things which you have to keep in mind. Okay, heat is a boundary phenomenon. Suppose here, if I would have given you another tricky question, that inside there is a heat source, okay, and suppose there is a point A, there is another point B, and from A to B there is some heat interaction taking place, say 10 kilojoule. It is very very high than this too. Okay, I'm just telling, this is an imaginary number, and they will ask you what is the what you call heat transfer from the system, or heat transferred into the system A, considering the system as A. Sorry, I have given the same name, let it be P and Q. And in this case, this 10 kilojoule, even if it is greater than this two, this will not take into account, because it is a boundary phenomenon. They have not told that this 10 kilojoule any part is transferring into the E. Whatever is transferring may be because of this 3. Okay, is there any doubt here? You have to always keep in mind that heat and work, these are boundary phenomenon. Okay, now taking the system as A, so you have to take the Q in 10 plus and this 30 joule, and then you have to take the Q out, that is this is my first part. Okay, you have to take the Q out, and Q out is my 20. So Q in will be my positive and this will be my negative. Okay, so the rest, my Q net will be then it will be 20 joule. So what will be your answer? The answer will be system gains 20 joule. Okay, any doubt? Okay, next 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 let us move to the second part. It will be very very easy, because seeing the first one you have understood, it will be very very easy. So in the second part, you have to just consider B as the system. Forget about whatever thing is happening, you just focus on B, whatever things are happening in this part B. Okay, and you have to look the boundary, all the boundaries of the B, whatever heat interactions are taking place in the boundary of the B. Okay, so now for B, Q in, okay, my Q in will be this 20, only 20, yeah, because the others arrows are going away from. So my Q in will be 20 joule, and my Q out will be my Q out will be 10 plus 30, 10 plus 30 joule, that is my 40 joule. So what will happen to the Q net? So this will be having a negative, since going out is always negative. Okay, so this will be minus 20 joule. What does this mean? This means that system B loses 20 joule. Okay. Yeah, okay. Now the third part is that you consider A and B entirely as a system. Okay, now you consider A and B entirely as a system. So if I consider A and B together as a system, let me change this color. Okay, I'm taking this purple color as, okay, the A and B together as me and as my entire system. Now for the part C, Q in, you just have to focus on the boundary. Okay, inside only this 10 joule is coming. Okay, so Q in is equal to 10 joule, Q out is also, I think it is equal to 10, yeah, it is equal to 10 joule. So and this will be with a negative sign, so that's why my Q net will be 0. That means there is no heat interaction, okay, for this A and B combined system, there is no heat interaction with it, with the surrounding. So this is how you should approach, this is how you should draw your system boundary, and then you have to consider, I mean you have to see whether heat is flowing in or heat is going out. Now in order to move ahead, we should know some other terminologies. Okay, now what is a state? Now state is something that tells us the condition of the matter. Suppose that one, suppose it is at state 1, or it is at state 1. So what do you mean by state 1? Now this tells us the condition of the matter. Now what do you mean by condition of the matter? These conditions of the matter, I can say that suppose this is my matter. Okay, this is my matter. Now any this is a box A which contains some matter, and I am saying that my box A is hot. This is a state of the box. Now is it some quantitative does it give anything about the what type of hot? Is it hot? What type of hot? Is it hotter than something, or by hot means what? Because hot, cold, small, large, these are all comparative quantities, okay, comparative terms. That is why now to define this state of the matter properly, we have some macroscopic variables. Now these macroscopic variables are called the properties of the system. For example, temperature. Okay, now if I say that this temperature of this box is 30 degrees Celsius, now this is 30 degrees Celsius for you, this is 30 degrees Celsius for me, this is 30 degrees Celsius for the every person who is coming and measuring with the same same thermometer and for the same box. Okay, but this box may be hot for someone, may be cold for someone. Okay, so that is the difference between state and property. Property gives you the quantitative or the exact analysis of the, like what you call it, it can quantify what type of thing is it can be. Okay, now one more thing, that what do you mean by macroscopic variables? Macroscopic variables is because that this thermodynamics, okay, this approach, whatever you will be studying in engineering thermodynamics, this thermodynamics is basically a macroscopic approach. It means that suppose this temperature is 30 degrees Celsius, it directly assumes that each and every point of this box is 30 degrees Celsius. Okay, now you may have a question that, sir, this is not at all possible that at each and every point this is having 30 degrees Celsius. Yes, there may be variations, because that delta T by delta X, okay, or delta T by delta Y, that gradient in temperature, that may be what you call that may be present. But if that gradient is say 0.001, okay, 0.002, after point, if there are two zeros, we consider this one as 0 only. Okay, so if this is very very small, you can easily neglect. Okay, this may be some 29.9999, what effect it will make in your calculation. Okay, so it is better if you take entire this one, but this is not valid if this del T by del X is very very greater. Okay, you should keep in mind this thing. Okay, now that is why macroscopic approach of thermodynamics is studied. Another thing I just want to tell, this may be quite a bit away from the syllabus, but this is mostly asked in some interviews. Okay, thermodynamics, the name itself is a misnomer. Okay, you will be studying thermodynamics, but whatever system you will be taking, this will be quasi static. That means it will be almost static, there will be not at all anything in dynamics. Okay, so this is this is the biggest misnomer that we study in thermodynamics. But even if you do the dynamic phenomenon, you will get only a little variation in your calculation, which you will be studying in higher class. Okay, sorry for going too much ahead. Now next is what? Change of state. So whenever, now a property is what? It is a macroscopic variable that can define the state of the system. Now suppose that property value is changing. Now you did some work, you did some heat transfer, you did some whatever thing you want to do, and after that this temperature of the body changed from 30 degrees Celsius to say 40 degrees Celsius. Okay, now this macroscopic property got changed. Now this change of the macroscopic property is called the change of the state. Okay, the change of this macroscopic properties, that is called the change of the state. Okay, now this uniform state, this is what I have already told you. If the properties of a system at a particular time is invariant in space, okay, suppose at a particular time, say at 3 o'clock, you measured the temperature of this box, and at each and every point of this box you got 30 degrees Celsius, that means this is in a uniform state. Okay, next is what is the steady. Yeah, hello.
Sir,
Yeah,
sir, now I am disconnecting, sir. After 10 minutes, I will joining, sir. Please confirm, sir.
yeah, okay, fine.
Aspect
Yeah,
manager.
okay. So steady state, if the properties of the system, it will does not change with time. Okay, this does not mean that I am not telling you it will not change in space. Okay, these two are a bit tricky to understand, but you just have to keep in mind uniform deals with spatial variation and steady deals with temporal variation. If the properties of a system do not change with time, we consider this as a steady state, and if the properties of the system do not change in space, then we call it as a uniform state. Okay, now process see, uh, it is going from 30 degrees Celsius to 40 degrees Celsius. Let me draw it. Okay, you will understand. Imagining is a bit difficult at this stage. You have to do a lot of thermodynamics if you want to imagine. Someone is coming. Okay, fine. Now process, what is a process? Actually, again, this process is also a misnomer. Okay, the definition of process is what, that suppose a body undergoes a change from state 1 to state 2. Okay, and it goes through a number of states. Now it will go through a number of states, and you will join all these states, because it went from this state to this state, and then finally it come to this state. Now this is what we call as a process. Okay, and actually what I am drawing, this is a reversible process. So process itself means a reversible process. Definition of thermodynamics what earlier scientists gave, according to that, irreversible process is not at all a process. It is just given a name in order to say you that there exists some, I mean, opposite terminologies also there, and based on that which you could not do. Okay, so that's why whatever, but here in this entire course, but you just have to keep in mind these are the things which you will be facing, in Viva. Okay, after 4 years or whatever year, if you are interested in further studies, you will be facing such type of problem, such type of questions. Okay, so process, it's that the part from which the change of state takes place, and if this process may be reversible or this process may be irreversible. Now when can you say a process is reversible and when can you say a process is irreversible? Okay, now suppose from going from point 1 to point 2, there are number of states, and you know each and every state. That means between these 2 points the gap is very less. Okay, the gap is very minor. Now if you go from point 1 to point 2, there are infinite number of steps, and you know each and every step. That means at each and every state they were in thermodynamic equilibrium. I will come back to you. They will be in thermodynamic equilibrium, and that is why you could get a point there. Okay, so then this type of process is called reversible process, because you can go back to the entire path again. Suppose there are some weights here. Okay, there are n number of weights. Okay, and you will put one by one all above it very slowly, and you will measure, and this difference between the weights is also very less. Okay, and you will put one by one and very slowly, and then such slow processes are called quasi static processes, and at each and every point you are getting measurement. Okay, so this is what these are, these points. Okay, so such, and then if you join from initial to the final state, this is what we call it as a reversible process. Okay. Now then based on this you know that okay, now one more thing I have to tell you. I have told you that thermodynamic equilibrium. Now what do you mean by thermodynamic equilibrium? Thermodynamic equilibrium is the combination of mechanical, chemical and thermal equilibrium. So before going to the problem, let us say that what is thermal equilibrium. Thermal equilibrium by the name itself, temperature same. Okay, now if body A has same temperature as that of body B, then these two bodies are called in thermal equilibrium. These two bodies are said to be in thermal equilibrium. Then what do you mean by mechanical equilibrium? Now if the pressure at the body A is equal to the pressure at the body B, then this is called mechanical equilibrium, because we know that if there is pressure difference, particles will flow from high pressure to low pressure, because of which there will be some dynamical force. This type of dynamics, the mechanics comes into picture when motion is there, yes or no? So this type of equilibrium is called mechanical equilibrium, when the pressure difference is the same. Pressure is same between 2 points. Next, what do you mean by chemical equilibrium? Chemical equilibrium means,
Sir,
yeah.
sir, can you reverse one time, sir, that from first onwards, if you don't mind?
Which one?
From whatever concept you have done so far.
Oh, this will be uploaded in the video, don't worry. You just go back, I can't reverse it. Okay, you just continue. If you don't understand, you can ask me from the present topic, whichever you have joined. Okay, and the
Okay,
reverse
sir.
one you will get, it will be uploaded in NPTEL and my personal YouTube channel, which I will be giving you. Okay.
Okay, sir.
Okay, so chemical equilibrium is what? Suppose there is some concentration of some particles. Suppose this body A and B are together, and concentration of A is equal to concentration of B. Okay, suppose some whatever it may be, any gas whose concentration, and so there is no flow of this what you call matter from A to B, then such type of equilibrium is called chemical equilibrium. Now if a body is comprising of the entire these three equilibrium states together satisfies, then this body we call it as a thermodynamic equilibrium, which I call it as TD equilibrium. Okay, thermodynamic equilibrium. It should be mechanical equilibrium, it should be thermal equilibrium, and it should be chemical equilibrium. Now let us try to solve this problem. Now there is a container, and it has some gas, and it has a movable piston. Now forget about how this piston move from this place to this place. Okay, forget about where the heat input in going from the piston from the state 1 to state 2. I'm just telling you that it has gone from state 1 to state 2, and that too in a quasi static process. Then how will you draw the process diagram? Okay, so the answer is, it can be any property. That's why I have not mentioned heat, work. It can be any property. Say this is property 1, and this is say property 2, and suppose this is my state 1, and say this is my state 2. Okay, now it is going from state 1 to state 2. It can go by any direction also. Okay, it should not be like it is bending this side, it can be bending this side. Only I am interested in saying whether this process is reversible or not, because I cannot directly solve your assignment problems. I can just give you hint. So this is how you can see whether the process is reversible or not. If the process is reversible, that process should happen quasi statically, and if the process is not reversible, then it will not take place quasi statically. Okay, I will come back for an irreversible, but since this is a reversible process, you draw any part, and that too in a solid curve. Because why? Because you know each and every point that exists between these 2 points. That's why it is quasi static, and each and every point from here to here, when it went, at each and every point it stopped, and at each and every point you have taken the measurements of the parameter P1 and P2. Understood? That's why you have got a very very smooth curve without any break. Okay, now yeah, now an ice bar, it is kept in an open atmosphere such that the ice bar melts and forms water. Okay, and if the solid and the liquid states are assumed to be state 1 and state 2, then you have to draw the process diagram of melting of ice. Can you try? You should not mention any temperature, you should not mention any pressure, you should only draw two parameters P1 and P2, and you should show the diagram for going from state 1 to state 2. Okay, so now since this is an irreversible process, how you know this is an irreversible process? Because okay, there are some things you should keep in mind. If anything takes place due to finite temperature difference, finite means that difference of temperature is such that you can't neglect. Okay, so such type of temperature difference, if because of that such type of temperature difference, if that process takes place, then that process is always an irreversible process. Same is the case, suppose some work done is taking place because of finite pressure difference, then that type of pressure difference is that type of process is also called, and process is also called an irreversible process. Now same, I will not draw any pressure or temperature. So since this is an irreversible process, you draw state 1, you draw state 2. Okay, now in between you don't know how many points are there, so you give a dotted line. So what I was trying to say is that irreversible processes are always expressed by dotted lines, and reversible processes are always expressed by solid lines. Okay, because you know each and every point of the processes. Now we have studied properties. Now the properties, there are two types of thermodynamic properties. Types of thermodynamic properties. Now properties can be intensive and properties.
Sir,
Yeah,
in previous problem, you are telling us it is an irreversible process, no, sir?
yeah.
Sir, how, sir, it will be irreversible process?
Oh, so if the see, this is taking entirely because of heat transfer. Yes or no? The ice is melting because of the heat transfer. Okay, and this
Oh,
heat
okay,
transfer
okay.
is because of a finite temperature difference, isn't it? So if there
Yes,
is
sir.
a
So
fine, yeah.
temperature can't be reversed, right?
No, no,
Like that, sir?
no, no, no. I'm not telling that. Okay, I'm not telling that temperature can't be reversed. I'm telling that this is an irreversible process because this heat transfer is taking place because of finite temperature difference. It's not infinitesimal temperature difference. If it would have taken place very, very slowly, okay, infinitesimally, then you could have told that okay, at each and every point I know the values of the temperature. See, infinitesimal means what? It takes place very, very slowly. Okay, then only at each and every point you will get the values of P1 and P2. Yes or no? Got my point?
Oh, yes, sir. Yes, sir.
Yeah. Okay. Then yeah. So types of properties. There are two types of properties: thermodynamic properties, intensive properties, and extensive properties. Intensive properties are what? Those properties which are independent of mass. And extensive properties, these are dependent on mass. Okay, now intensive properties, there are examples like temperature, pressure. Okay, and can you tell me any extensive property example?
Specific volume, sir.
No, 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 specific volume, it will be an intensive property, I think. Specific, no?
Oh,
All specific properties are intensive properties.
pressure, temperature, and all intensive properties.
Intensive properties, because these are independent of mass. Because if I measure the temperature of this entire box, or if I measure the temperature of this part, it will remain the same. Because thermodynamically we assume it as a macroscopic equilibrium, that's why. Okay, so extensive properties, example.
Extensive property. I don't know, sir.
Any property, you just think any property that is dependent on mass. Just think about any of the property. If you increase mass, that property may change, and if you decrease mass, that property may change. Just think, you can think, it is very easy.
Mm, Specific enthal.
No. Those specific enthalpies, those are all intensive properties. Those are not dependent on mass. Okay. The first thing is that extensive properties depends on mass. The mass itself, now we can tell. If you increase the mass will increase. If you decrease the mass will decrease. Okay. But sometimes the people, it's not easy to digest.
Energy also.
Yeah, this is not
Internal energy.
no, internal energy, I will come back to those internal properties, don't worry. Okay. Yeah, internal energy is true, specific internal energy is not true. Okay, internal energy, the capital U you are talking about, that this is extensive property. Then enthalpy, this is an extensive property, but don't go too far. Volume is not it. Hello. Okay, sorry for the network interruption. Okay, so specific, yeah, so extensive properties, what I was telling, yeah, volume, because if you increase mass, the volume will increase, and if you decrease mass, the volume will decrease. Okay, next is, we will try to we will come to another important topic, and that is the pressure, measurement of pressure. So before that, we have to know what are the different types of pressure. Okay, now uh, yeah, the first one is the atmospheric pressure. Atmospheric pressure. Okay, so it is the pressure of the atmosphere. It is the pressure of the atmospheric air. That means whatever pressure the atmosphere exerts on it, and that is the pressure, atmospheric pressure. Okay, then next is the gauge pressure. Gauge pressure, it is the pressure measured by the pressure measuring gauge. Okay, so the pressure measuring gauge, whatever it will give you the pressure. And then the third one is the absolute pressure. it is equal to P atmosphere plus P gauge. Okay, P atmospheric pressure plus P gauge pressure, that is equal to your absolute pressure. Now next is that one important thing in order to solve pressure related problems is you have to understand the hydrostatic paradox. Hydrostatic paradox, this means that if a liquid is at rest, okay, then the pressure of that liquid is from the surface, from the level of the water. Okay, suppose this is a liquid, specifically this is a water, and you want to measure the pressure at the point A, pressure at the point B. What you will get, that pressure at A is equal to rho into G into H, and pressure at B is equal to also rho into G into H. What it means is that it does not depend whether it is here, whether it is here, whether it is here, whether it is here. It only depends on the height from the level of the water. So if you know the height, you can calculate the pressure at each and every point of here. Okay, so this is the hydrostatic paradox. Because of this only we can solve the pressure measuring problems. But remember, this is the hydrostatic paradox. That means the condition is that the fluid should be at rest. That is why this is not applied when a gaseous particle is there. If we want to measure the pressure of the gases, then we have to do some other tricks. Okay, even if the density is provided. Now one more very important thing is that for the hydrostatic paradox, suppose the fluid is full till here, and suppose here also, I'm sorry, yeah, so these two, you might feel that their volume, whatever is different, whatever everything's are different, but since these heights are same, so if you want to measure pressure at P and pressure at Q, the pressure at P will be equal to pressure at Q because of this hydrostatic paradox. Okay, and based on this only we can solve the pressure measurement using the whatever U-tube manometer or single tube manometer or inverted U-tube manometer. Now we will be trying to solve some of those problems. Now first is a gas is flowing through a pipe, okay, and its pressure is measured with mercury manometer with its one limb exposed to the atmosphere. And okay, so suppose this is a pipe, I'm sorry, very bad pipe. Suppose this is my pipe, okay, and what is called gas is flowing, okay, gas is there, and the difference, okay, then there a mercury manometer is attached, and the other part of this is exposed to the atmosphere. Okay, so here the gas is flowing and the other part is exposed to the atmosphere. Now what is called that the difference in height between the two limbs of the mercury manometer, suppose this mercury is lifted here and this difference is height, this is given HS 460 millimeter. Now you have to find the pressure of the gas. That means okay, since this is the opening, so gas will come here also. Okay, so here you have to what you call you have to take into consideration this hydrostatic paradox. Okay, what we know that since this is a mercury fluid. This gas is always in a motion. Okay, so this gas is always in a motion, but this part is in rest, na? So but we cannot apply here because this is not a liquid, this is not a liquid. So we will apply this part here. So we will take the base this to height. Okay, let me change the color, then you will understand. This means that this entire at this line, wherever you go, you will feel the same pressure if the liquid whatever liquid or gas is or whatever liquid or gas is above you. Okay, this is the hydrostatic paradox. Okay, now suppose I am naming this as A and I am naming this as B. Okay, this means question is telling that this one is exposed to atmosphere, that means this is my P atmosphere. Okay, this is exposed to atmosphere, this is my P atmosphere. So this means what? Pressure at A is always is equal to pressure at B. What is pressure at A? This is what? This is my gas, and this gas is only coming and coming till here, no? So this pressure at A is nothing but my pressure at the gas, pressure applied by the gas. Is it clear? Hello?
Yes, sir.
And then we need to calculate the pressure at B. Now pressure at B, it is this pressure P atmosphere plus whatever this fluid that is above this point B, it will apply. So pressure at the point B will be equal to P of atmosphere plus this one rho of what? This fluid. Yes or no? Because this fluid is only there, so that will be rho of mercury into G into H. Is it okay? Now what is the atmospheric pressure they have given? Atmospheric pressure is given, it is given that 760 mm of mercury. So 760 mm of mercury is equal to my atmospheric pressure. That means 760 into rho m into G plus this H is what? 460 into rho m into G. Okay, can you do the calculations? Remember this is in mm, so
Yeah.
you convert it into meter and then solve it, you will get your answer. So it will be 700 0.760 into rho m is my 13600 into Z is my 9.81. so yeah, plus then your 460 into 9.81 into 0.46 into 9.81 into 13600. Okay, so this will be around 1.6276 into 10 to the power 5 Pascal, and this one I can tell this one as 1.62 1.62 what happened? Hello? Oh, okay, admit. Okay, so this will be equal to 1 point what happened? Can you see my screen? Hello? Hello?
Yes, sir.
Can you see my screen?
Yes, sir.
I don't know why it is getting erased. Okay, I will open a new PowerPoint presentation. Okay, so yeah, so that answer, the previous answer was okay. Let me come, since so many students joined again. So what we were doing, we were trying to solve, and we were trying to calculate the pressure of this gas flowing here. Okay, and the manometric fluid was mercury, and the manometric fluid limbs, this height difference was given to us, that is equal to 460 mm. Okay, and this is my rho mercury, and which is equal to your 13600 kg per meter cube it was given. And we have to measure the pressure of the gas, we have to measure the pressure of the gas. So according to hydrostatic paradox, so you go from at this point, wherever you go, you will get the same pressure. This same thing is applied for each and every point. If you go here, I mean in the same vertical plane, you will get the same pressure, you will feel the same pressure everywhere. Okay, so according to hydrostatic paradox, that's why I have taken a point A here, I have taken a point B here. So pressure at the point A will be equal to pressure at the point B. Now pressure at the point A is nothing but the pressure exerted by the gas, because this is the gas only which is coming here. Okay, and one thing they are telling is that this thing is open to atmosphere, so this is my P atmosphere. Okay, so then my PB will be equal to PB will be equal to P of atmosphere plus rho mercury into G into H. Okay, so P of atmosphere they have given as 760 mm of mercury. Okay, so it is there in the previous question, which I will already upload, don't worry. And so 760 mm, so this means that 760 into rho m into G plus 460 into rho m into G, and this will give you your 1.62 bar. Is there any doubt in this question? For those who came late also, I can go back if you wish. Hello.
No, sir.
Okay, fine. So let us then modify this question a bit. Okay, okay, so a differential manometer, it is used to measure the pressure drop between 2 points, and in a process line. Now this contains water. Okay, and the specific gravity of the manometric fluid is 1.05. so here there are two things. First thing is that uh, earlier it was gas, remember, earlier it was gas, so we had no issue. But now what is happening? Okay, but now liquid is flowing. Now this is water, so water is flowing here, and okay, now water is flowing here. Let me use different color, then it will be good, I think. So I am using blue color for water, don't get confused. So water is flowing, and here also it will be all water. Now this is not open to your what you call atmosphere. Okay, this all entire water, and this side also it is water, and this is the my manometric fluid. Okay, now they have given that the specific gravity of manometric fluid is 1.05. So what do you mean by specific gravity? Specific gravity means density of fluid divided by density of water. Okay, so that means it is just a ratio, a specific gravity of fluid, of any fluid is equal to density of the fluid divided by density of the water. Now in our question they are giving that the specific gravity of the manometric fluid is 1.05, which means that my rho m is equal to 1000, which is my density of water, into 1.05. So this is what 1050 kg per meter cube. This is the first thing. So we are into the pace of the previous problem by getting the density of the manometric fluid. Instead of the specific instead of density directly given, they have asked us to calculate the density of the fluid by giving us the specific gravity of the fluid. Okay, now the second most problem in this case is that it is not open to atmosphere. How we will do? Okay, and the third thing is that this is a liquid. Okay, oh I'm sorry, third thing is that this is a liquid, and they have given the measured levels in each arm. Okay, whatever measured levels, that means this 374 mm and 382 mm, what are they? I am just telling you. Suppose you had some reading here. Okay, this is just a manometric and this is some reading scale, and in this reading scale you have got this height. When in this height you have got the reading as 382 mm, which is exactly how you will get to do in your lab sessions. Okay, so you will get to measure the heights only, you will not get directly the difference of the height, the difference of the two manometric liquid. You have to calculate the difference and then you have to do the sum, and you have to get this 374 mm. So this height is your 374 mm. Okay, you have measured with this scale that is provided in your manometer, and from that scale you have got this height to be 382 mm and this height to be 374 mm. Now there are 2 points they have given. This is the point 1 and this is the point 2. What you have to do, you have to calculate the pressure difference between point 1 and pressure difference between point 2. This is the question they have asked. Is the question, we can't insert anything else on slide 2 because the web version. Okay, is it clear? Yeah, okay. So now yeah, this was the question that was provided. Then specific density is given, specific gravity is given to us. Now the next thing is that we have to calculate the pressure difference between the points 1 and the pressure difference between the points 2. Now just like the previous case, what will we do? I have to draw this again. m is my 1050 kg per meter cube, and this is my point 1, this is my point 2, and at this my height given is 382 mm, 382 mm, and here the height given is 374 mm. So, and here it is water, this H2O. Okay, so now according to hydrostatic paradox we will start again. So we will take the baseline where the pressures will be equal. So I will take a point A here, I will take a point B here, and we will know that pressure at the point A is equal to pressure at the point B. Okay, now then we have to take into account what is the pressure at the point A and what is the pressure at the point B. Okay, now what are the things that we know? Okay, now pressure at the point A will be, suppose I am taking this distance as x, and say this distance as h. So what will be my h then? My h will be 382 minus 374 mm. What is this? 382, 374, this will be my 8 mm. Okay, this will be my 8 mm. Now then P at A, can I write P at A is equal to P1 plus rho W into G into H plus X, and pressure at B, can I write this one as P2 plus rho W into G into X plus rho M into G into H. Okay, so pressure at A, it will be equal to pressure at the point 1 plus rho W, because this entire place is filled with water, so that is why this is rho W into G into rho W into G into H, because this distance is H plus X, no? So this is rho W into G into H plus X, and pressure at the point B is equal to P2 plus rho W into G into X plus rho M into G into H. Now what we need, we just need P1 minus P2, so very easy, we know that PA is equal to PB, put it here, and then you will get some cancellation terms. Okay, let us do that. Okay, what we can do, PA is equals to PB, so P1 plus rho W into G into H plus X, this is equals to P2 plus rho W into G into X plus rho M into G into H. This is what we got from the previous one. So that PA is equal to PB, so we need what? P1 minus P2, so P1 minus P2 will be equal to, now this is what, rho w into g into x plus rho m into g into h minus rho w into g into h minus rho w into g into x. Okay, so here rho w into g into x is gone, so what is left, g into h I can take it as common, so this will be rho m minus rho w. So what is g, 9.81, what is h, is my 8 mm, so 9.81 into 0.008, and rho m is my 1050, and this is my 1000, so this will be equal to Pascal. Okay, so 9.81 into 0.008 into 1050 minus 1000, so this will give you the answer. So this, the pressure difference is 3.924 Pascal. Okay, so the pressure difference is your 3.924 Pascal. Okay, now suppose in this there was a mixture of suppose instead of water, if this would have been a gas, then what would be the difference between P1 and P2? Okay, this one you can try this one at home, that instead of this one, if it would have been the difference between P1 sorry, if the instead of liquid water, the flowing fluid would have been a flowing fluid have been a gas, then what would be the difference between P1 and P2? Now I'm sorry, yeah, now next there will be something which we will be dealing with, pure substance and pseudo pure substances. Okay, so that will come when we will be solving sums related to psychrometry, that is the mixture. Now what we'll be doing that, when what do we mean by pure substance, that pure substance, what is mean by, okay, sorry, I'm sorry for this one. Okay, I will do this, yeah, so insert text box. Okay, pure substance. So what is a pure substance? So a pure substance is as one which is it is having identical molecules, okay, that means there is no mixture, it is having identical molecules throughout the throughout its entire mass, if it is having identical molecules. And if it is impure, or if it is not pure, then it contains mixture. So what is that, when there is air is basically a mixture of oxygen, nitrogen, many other types of gases. So but in this particular chapter we will be taking this air as a pure substance, because of whatever reason you will understand this in details when we will be doing this one psychrometric classes. Okay, now let us do one more problem. Yeah, so Now what will be the gauge pressure P gauge of the gas? Okay, so till now we were doing just pressure. Now you will understand from this that whatever we were calculating, was it gauge pressure or was it absolute pressure, whatever, was it vacuum pressure, whatever pressure was that. So this gas is flowing this side, so I'm taking blue color as this gas. Okay, so say this gas is here, this gas is everywhere, and this is open to the atmosphere, so that is P atmosphere is there. Okay, now yeah, once again let me come back here. Here we have calculated P1 minus P2, isn't it? Now can see what is it the difference between the gauge pressure, or there was one question in your assignment, so you can try this. Is it the difference between the gauge pressure or is it the difference between the absolute pressure? Now just think about that. Insert new slide. Okay, so is it the difference between, what is the definition for P absolute? It is P atmosphere plus P gauge. Okay, so suppose this P1 is my P1 absolute. Okay, then what it will be? It will be P atmosphere plus P1 gauge. Similarly, P2, if it would have been my P2 absolute, then P2 absolute, then it will be P atmosphere plus P2 gauge. Okay, so now if I do P1 minus P2, then this P atmosphere terms are same, so it will be P1 gauge minus P2 gauge. So in case of difference, it doesn't matter whether the difference is between P absolute or P gauge, because ultimately it will remain the same. Okay, this one you should keep in mind. Now coming back to this question, yeah, manometric fluid is mercury and its density is provided, and this gas is there, and suppose what happens if in this previous question which we did in the first place, in the previous question, in this case the density of the gas was not given to us. Suppose now you have the density of the gas is also given to you. Let me tell where is there. Yeah, suppose the density of the gas is given to you as 100, which is very high, but I'm just telling you, if it is given the density of the gas, what would be the change in the problem? Now if the density of the gas is provided to you, then you can't ignore that hydrostatic one. Okay, so now same thing we will go as in the previous case. We will draw a line where the pressures will be the same. I will take this point as A and I will take this point as B. So the pressure at the point A will be equal to the pressure at the point B. Now in this case, if you are asking me to calculate the if you are asking me to calculate the pressure of the gas, gauge pressure of the gas, then you have to see this one. Suppose then you should also tell, you should tell from which point, at which point you want to calculate. Okay, suppose I want to calculate at the point 1, because now at each and every point it will be different, because the density of the gas is provided to you, so rho g into h effect will come into picture. Okay, now I want to measure the gauge pressure of the gas at 1. Okay, so you want to measure the gauge pressure of the gas at 1. Now similarly you have to do, you just have to treat this one as another liquid, which is in the previous case. So P at A is equal to P at B. So P at A will be what? P at A will be let me move to the next slide. So my P at A, this will be equal to P1 plus rho g into this height, this total height. Now let me assume that this height is x and this height is h. Okay, so then this will be my rho g into h plus x. Okay, then my pb, it will be p atmosphere plus rho m into h. P of atmosphere plus rho m into, I'm sorry, g is left here, g is there, sorry, yeah, rho m into g into h. Okay, so now I will put it here. PA is equal to PB. So what is PA? PA is P1 plus rho GH plus rho G X. Okay, and then this will be yeah, then this will be my rho m, sorry, PA plus PA plus rho m g into h. Now what I was trying to tell you, that now you want the gauge pressure, this means what? P1, that is what P1 is, what you want. Now you will have to know the value of x. In earlier case, when we were dealing with the liquid case, since the same liquid was there here also, so this x got cancelled out here. Okay, but in this case you also require the value of x to be given. Now let us suppose this value of x that is given here is 24 mm. Then what will be your answer? Your answer will be rho of the gas is given as 100 into g into your this h is what? H will be 225 minus 200, that is equal to your 25 mm. Okay, so this h is 25 plus rho into g, so 100 into g into your x is given as 24, okay, mm, and this will be equal to p atmosphere. P atmosphere is, we all know that 760 mm of mercury, so this is 13600 rho of mercury into g into 760 plus, and rho m 13600 into g into this is what we call it says 25. Okay, now then yeah, so then next it will be uh, P1, this will be equal to, we just put all the values here, so 100 into 9.81 into 0.025, 24.25, sorry, plus 24.25. Okay, and this will be 23.55, 23.54, and this this will be equal to 13600. Okay, 13600 into 9.81 into 0.760, 1.013 into 10 to the power 5, 0.013 into 10 to the power 5, and this will be 13600 into 0.025. 3335.4. So 1.013 into 10 to the power 5 plus 3335.4 minus 23.544 minus 24.25. This will give you P1 is equal to 1.04 into 10 to the power 5 Pascal, or this is what, 1.04, I'm sorry, 1.04 bar. Okay, now this is your gauge pressure. Now if you want to get your absolute pressure, you just have to put P absolute at the point 1, that will be equal to 1.04 bar plus 1 bar, and this will be equal to 2.04 bar. Yes, so that will give you 2.04 bar. Okay, now same question, this part, if we can do this thing, entire thing in a liquid. Okay, this is water, and this has a density of 1000, and this manometric fluid, its specific gravity is 1.05. Okay, and the difference between these two, this H is given to you as 5 mm, and this distance is given to you as 5 mm. Okay, so same thing we have to do, and here also if you want to calculate the pressure at the point this one, then you have to do the same thing. So whatever, if it is liquid or if it is gas, only if the gaseous density is not given, then whatever the gas pressure, suppose if it is filled at this point, it will be the same at this point. But now here this thing will be entirely different. So this one, let us try together. So since this is water, so now we will do the datum again. So this is the datum, so this is the point A, say this is the point B. Okay, so pressure at A will be equal to pressure at B according to hydrostatic paradox. Okay, now what is pressure at A? Pressure at A is equals to rho of water, sorry, first pressure is what, this pressure is P1, so pressure at the point 1 plus rho of water into G into H plus X. Okay, and what is the pressure at the point B? Pressure at the point B is pressure of the atmosphere plus rho of manometric fluid into G into H. Now you have to equate these two and you will get the value of P1. Okay. So what you will do, P1, so PA is equal to P1 plus rho of water is 1000 into 9.81 into H5 plus X also it's 5. Okay, and PB is pressure of atmosphere plus manometric fluids specific gravity. Again, specific gravity is 1.05. What is this meaning? The meaning is that density of the manometric fluid is 1.05 into 1000 kg per meter cube, that is 1050 kg per meter cube. Okay, so then this will be 1050 into rho into G into H, into 9.81 into 5. Okay, then I will equate this P1 plus 1000 into 9.81 into 10 mm is equal to 0.010, and this will be equal to 1050 into 9.81 into 0.005 plus 1.013 into 10 to the power 5. Okay, now then P1 plus 1000 into 9.81 into 0.010, this is 98.1. okay, then next is your 1050 into 9.81 into 0.005, this is your 51.5, and this is 1.013 into 10 to the power 5. So what will be your P1? Your P1 will be 1.013 into 10 to the power 5 plus 51.5 minus 98.1, that will be your 1.12 into 10 to the power 5 Pascal, that means that 1.012 bar. So this brings almost to the end of today's class. So let us quickly revise what we have understood. Okay, so in the first we studied what is a system and what is surrounding. System is one where our study is focused, and surrounding is one which is the entire thing that is external to the system. The system and the surrounding, they together constitute the universe, and the system and the surrounding, they are separated by a boundary. Now this boundary may be real or this boundary may be imaginary. The second thing is that heat is a form of energy, and heat is a form of energy that takes place only because of the temperature difference between the system and the surroundings. Heat is felt only at the boundary, that means it is a boundary phenomenon. Now numericals we did, and we understood that heat, the sign convention that is followed for thermodynamical problems is that whenever you add heat to a system, it is positive, and whenever you remove heat from a system, it is negative. Now work done according to thermodynamics definitions, work done is done by work can be done by a system, or it is said to be done by system whenever the sole effect that is felt on the surroundings, it can be changed, or it can be used for raising the weight. Okay, now in other case, or from layman's terminology, whatever energy transfer that takes place not because of temperature difference, that is called work. That means for because of temperature difference, the energy transfer taking place is called heat. So whatever energy transfer that takes place other than the temperature difference, this is called work transfer. Again, just like heat, work is also felt at the boundary. That means it is only a boundary phenomenon. Now work sign convention for numericals is that whenever work is done by the system, it is positive, and whenever work is done on the system, it is negative. Now we went in to see that the different types of the system, and once again it depends on which system you choose. Okay, now open system is one in which mass interaction takes place, energy transfer may or may not takes place. Okay, closed system is one in which energy transfer take place but mass transfer do not take place. That means whatever the mass is always conserved there. And then isolated system is one in which the neither mass nor energy transfer takes place. And then universe is a good example of isolated system. People often say that thermoflux is a type of isolated system, but you will never find any thermoflux which will not allow any form of heat transfer, because there will always be a temperature difference between the surrounding and the inside the thermoflux, and not a pure insulator is found in this world. We have to go to another some millions and millions of ages, and then might be coming a very good insulator, but there is no a proper insulator which can prevent heat from flowing. Okay, so rather than giving thermoflux as an example of isolated system, please try to give the examples of what you call universe. You give the universe as an example. This is what I said, that considering a system, suppose the wire, inside the wire electrons are, we know that electrons are flowing inside the wire, but if we consider the entire wire as the system, no mass flows through the system. So then we solved different problems, say like in case of open lead, in case of fixed lead, in case of movable lead, what type of energy transfers are taking place, and what type of approach should we do, control volume approach or control mass approach. Then we dealt with this heat transfer taking into consideration. Then we define what is a state. State is nothing but whatever condition of the matter is it, and property is the macroscopic variables that helps us to define the system. For example, state can be like a box is hot or cold, but that box may be hot for me, it may be cold for you. But if I say that the temperature of the box is 30 degrees Celsius, it is 30 degrees Celsius for me, it is 30 degrees Celsius for you. So this is what is called property. Then if the system undergoes the change of property, we call it as the change of the state. Now this change of state, if it goes very very slow, and such that at each and every point we can get the values of the different properties of the system, then we call it as a process. Now processes of the thermodynamics can be of two types. It can be reversible, it can be irreversible. Again, irreversible process is a misnomer because it's never a process, but to make you understand, irreversible process takes place so fast that we cannot get points at each and every place. So that is why irreversible processes are depicted by dotted lines, and reversible processes, they are depicted by solid lines. Next, what do you mean by then we discussed about thermodynamic equilibrium. So a system is said to be in thermodynamic equilibrium if it is in thermal equilibrium, if it is in mechanical equilibrium, and if it is in chemical equilibrium. Now by means of thermal equilibrium, it means that by means of thermal equilibrium it means that the temperature of the temperature remains the same. If the two bodies A and B are in thermal equilibrium, it means that the temperature of the body A is equal to temperature of the body B. In mechanical equilibrium, it means that the pressure of the body A is equal to pressure of the body B. And chemical equilibrium, it means that the chemical concentration of the body A is equals to the chemical concentration of the body B. So if a system has these three equilibrium, that is chemical, thermal, and chemical, thermal, and mechanical equilibrium, then we call it as what you call thermodynamic equilibrium. Then we discussed about the different types of thermodynamic properties. Thermodynamic properties can be mainly classified into two types. It can be intensive or it can be extensive. Intensive properties are the one which are independent of mass, just like pressure, temperature, and extensive properties are those which are dependent on mass. such as volume, mass, internal energy, enthalpy, etc. But there are some specific properties like specific internal property, specific entropy, specific enthalpy. These are all intensive properties. All the specific properties are intensive properties. Then we discussed about the pressure. The pressures are various, there are lots and lots of things to be studied in pressure in other courses like fluid mechanics, but here we will be mostly dealing with atmospheric pressure, gauge pressure, and absolute pressure for your numericals. Absolute pressure is the pressure that is exerted by the atmospheric air on the system. Gauge pressure is the one that is measured by the pressure measuring gauge. It can be a manometer, it can be a inverted YouTube manometer, or it can be a simple barometer. And then sorry, barometer measures absolute pressure, I'm very sorry. Whatever other gauges, that is gauge pressure. And then absolute pressure, it is nothing but the summation of atmospheric pressure and the gauge pressure. Now in order to solve the problems for calculating the pressure pressures of a flowing gas or pressures of a flowing liquid, you have to understand what is hydrostatic paradox. Hydrostatic paradox says that I don't need anything to measure the pressure at a point A if at any point A, B, C, which are in this A or B, which are at the same vertical height, if I know the height from the level, okay, from where I want to measure. So and the condition is that the fluid should be in static. So the pressure at A is rho gh, the pressure at B is also rho gh, because this height is the same. Another the same thing, that these two containers look different but the height is same, so pressure at the point P is also equal to the pressure at the point Q. So yeah, so this is what and then we did different types of sums. I will be sharing with you all these solutions, and thank you for joining. Yeah, bye bye.